Okay, so first one is average rate of change. Okay, so you know, so whatever interval they want the average rate of change on, you only care about those x values. So they only care about this. So really, kind of, we're going to be looking at these points here that involve -3 and 3, and then that's it. And so now you just do slope formula with that. Um, and which way did they do it? Yeah, so they did. You could do it two ways. You could do, you know, y2 minus y1, whoops, over x2 minus x1. Okay, and then that ends up being b. So okay, yeah, so just remember, anytime you do average rate of change on an interval, this is always slope formula. Or not always, but a lot of times. Okay, next one they say, let f be the function defined by f of x equals e to the 2x. The average rate of change on f over the interval from 1 to b is 20, where b is greater than 1. Which of the following is an equation that could be used to find the value of b? Okay, so I say we just kind of set it up. Notice all the answer choices, they don't even really use the function. They don't use what the function equals, they just use the function notation, the name of the function. So let's set it up. So they say, just according to this sentence, they say the average rate of change of f over the interval from 1 to b, so just that on its own, is f of b minus f of 1 over b minus 1. And then it says, is 20, so equals 20. All right, and that's it. So that'd be C. Okay, next one. Let f be the function defined by f of x equals 2x cubed minus x. Which of the following expressions is the average rate of change? So another average rate of change of f on that interval. Okay, again, they use function notation, so it's just f of 3 minus f of 1 whole over 3 minus 1. Okay, so average rate of change on an interval is doing the slope between the two endpoints of the interval. Okay, so this next one. So I think this is the first time that we've had a graph of f prime and really trying to get information out of it. So you have to get used to, from now on you have to kind of notice what the graph represents. Sometimes it'll be f, sometimes it'll be f prime, every once in a while it'll be f double prime. But this is f prime. So we have no idea, unless we really thought about it, we have no idea what f looks like. But just kind of just see how we got to think about this. So think about if you just pick certain points. So I'm just going to pick random points here. So that point is -1, -1. And what this point represents is the fact that when x is -1, the slope of the tangent line on f, on the original function, is -1. So remember, all these points, if this is a derivative function, these y values represent slopes of tangent lines of the original function at this x value. Okay, so another point, say right here, 0, 0. Okay, this is saying that on the original function, when x is 0, the slope of the tangent line is 0. So it's saying, yeah, so just saying that. Okay, so just getting used to interpreting a derivative graph, I guess. So look at the question. So they say, let f be a differentiable function with f of 1 equal to -2. Okay, so this is just a single point on the original function. This is the point 1 comma negative 2. Okay, the graph of f prime, the derivative of f, is shown above. Which of the following statements is true about the line tangent to the graph of f at x equals 1? Okay, so just in general, anytime you have a graph and you have a line tangent to the graph at some x value, notice they always share this point. So this point here is on the tangent line, but it's also on the function. So that point gets shared by both. Okay, so if here they say, which of the following statements is true by the line tangent to the graph of f of x equals 1? So we know that this is a point on the regular function because it's f of 1 equals negative 2, so this is a point on the function. But if you're talking about a tangent line at the same x value, at x equals 1, then this point is also on the tangent line. Okay, so we know it's going to be either A or C because the tangent line passes through 1 comma negative 2. The tangent line at x equals 1 passes through this point. Okay, so we know it's not B and it's not D. Okay, and then we look at x equals 1, we look at the graph. And so notice at x equals 1, we have this point, 1 comma negative 1. So we interpret this point as when x equals 1, the slope of the tangent line is negative 1. And that's what this is saying. When x is 1, the slope of the tangent line is negative 1. Okay, so that's A. Okay, next one. So they say an equation for the line tangent to the graph of the differentiable function f at x equals 2 is y equals 9x minus 12. Which of the following statements must be true? Okay, so this is not the derivative. This is the equation of a tangent line to the graph at a certain x value, right? And on a function at every x value, there's going to be a different equation of a tangent line at every single x value. You know, it'll be its own little equation of a tangent line. So which of the following statements must be true? So think about, you know, we don't know what f looks like. You know, let's just say, so here's 2. So let's just say at, say the function looks something like this. And at 2, it's got this equation of a tangent line. Okay, so think about just this is y equals mx plus b. So this tangent line is this equation here. So the slope of this tangent line is 9, right? Just whatever that, right? Mx plus b. Okay, but remember the slope of the tangent line is at some x value is the derivative. So that means that f prime of 2, the slope of the tangent line at 2 equals 9. Okay, so that means that 3 is true. Okay, and then at x equals 2, so this point, if you plug it into the tangent line, you get 6. And so that means 2 comma 6 is a point on the tangent line. But remember, the function, the point on the tangent line shares the same point on the function. At least, you know, if this is the equation of the tangent line at x equals 2, then they share the point 2 comma whatever. In this case, 2 comma 6. So they share the point at 2. And since 2 comma 6 is on the tangent line, it has to be on the function also. 2 comma 6 is on the function, and that's what that means. F of 2 equals 6. 2 comma 6 is on f. Okay, but we don't know anything about the function at any other x value besides 2. So if they said f of 1 or f of negative 1 or f of 10, we have no idea. You know, f of 0 equals 12. If you plug in 0, you get 12. So that's a point on the tangent line. So that's a point, like if we looked at this example, that's this point here. So this this point here, this would be negative 12, that x value, that y value. So 0, 12 is a point on the tangent line, but we have no idea whether or not it's a function, a point on the function. Right? This function could do anything, and it may or may not pass through that point. So, okay, so 2 and 3 only. Okay. So next one, they say shown above is the graph of the differentiable function f along with the line tangent to the graph of f at x equals 2. Okay, what's the value of f prime of 2? So when they say f prime of 2, you interpret that graphically. So f prime of 2, graphically, this is graphically. The interpretation is slope of tangent line to f at x equals 2. So that's the meaning of just this little statement right here, this little notational, this function notation little expression means slope of the tangent line of f at x equals 2. That's what it means, at least graphically. So we look at the graph. So we need to find, when they ask us for this, they're really asking for this. So we want slope of the tangent line. So we have the tangent line at x equals 2. So we just need the slope of this line. And you could do different ways. You could just do rise over run. Rise over run. Okay, so pick 2 points. Just a reminder how to do it. Just pick any 2 points on the tangent line in this case. How much does it rise? It rises 1. How much does it run? Runs 2, so 1/2. Okay, number 7, they say the graph of a function f where f of b is greater than f of a. They're just saying this point is above this point. This y value, this point of this y value of this point is above the y value of this other point. As shown above for x between a and b, the derivative of f exists for all x in the interval from a to b, except at the endpoints, and except at 0. So 0 is a cusp, so not differentiable at 0. For how many values of c, they don't want to know what c is, but just how many values of c on this interval from a to b does this thing equal this thing? Okay. So first thing is figuring out what these things are graphically. Okay, let's start with the second thing here. So this is the slope of the secant line between the points a comma f at a and b comma f of b. So if you do the slope between these 2 points, these endpoints, that's what this right-hand side is. Okay, the left-hand side is the derivative of this function. Right. Okay, so this is like one of the definitions of derivative at a point, and this is at some point c. So this is a derivative of f at some point c. So, and think about derivatives graphically mean slopes of tangent lines. So think about this is the slope on the right is the slope of the line joining the 2 endpoints, which is the slope of a secant line, and this represents the slope of some tangent line at some x value c that's on this interval. So all this is saying is this whole problem is just saying they want to find out how many values of c is the slope of the tangent line equal to the slope of the secant line joining the endpoints. That's all this whole problem is saying. So let's look at like let's see if I can get this. So here's like the secant line, at least a segment, joining the endpoints. So that's the slope of the secant line. And we want to find all the values of x where the slope of the tangent line at certain values on the certain points on the graph have the same slope. So we want, having the same slope is parallel. So let's look at lines parallel to this. Okay. Let's take this line. So we want to know tangent lines. This is weird. That are parallel. So you notice if we come here and like go right there, right around there, notice that'll be a tangent line, and that's parallel to our original graph. Okay, so that means at this point, whatever this C value is here, the slope of the tangent line at this C value, the slope of the tangent line to the graph is the same as the slope of the secant line joining the endpoints, and that's what it's saying. So we found one of the values of C that makes this true. Okay, and then we just kind of keep doing stuff like that. Okay, maybe find another one. You see that right there? I'll kind of move it over just so it doesn't interfere with the other ones. So right there, right, there's another point C. We'll call this C1, C2. Okay, that tangent line to the graph is parallel. So maybe right there. Another one. These are all parallel. And then I should see one more down below. Right there. That's parallel. So notice these are all the C values that have tangent lines. All these tangent lines at all these C values whose slope is the same as the slope of the secant line joining the endpoints. And that's what that's saying. Okay, so 4 points. Okay, so let's look at these calculator questions. Okay, so for number 8, they say let f be the function given by this function. Of the following values of x, at which does the line tangent to the graph of f have the greatest slope? Okay. So derivative is slope. So when they say this phrase, have the greatest slope, they mean which does the line tangent to the graph of f and really it's really line tangent has the greatest slope. Yeah. So that phrase really means largest derivative value. Okay, so they're just saying if you take the derivative of this and you plug in each of these x values, which one's going to have the biggest value, right? Because derivative is slope. Greatest slope is greatest derivative. Same thing. Okay, so you can do it a bunch of ways. I did it, I think 3 different ways I did it in the calculator. So let's look at kind of, let's look at kind of some different ways to do this. Okay, so math, oh, so here, sorry. So notice I hit y equals up here. And then I'm going to type in the derivative of this into the calculator. So you can do math 8. I kind of did that quickly. So do math 8. That's derivative. And after you hit y equals. And then it'll put the derivative into y1. And so like the first function, y1, will be the derivative of f of x. So basically, when we put this in there, it's going to give us what's in y1 is f prime of x. Okay, so that's our function. And then we'll do x equals x. So that here, whenever you want to either graph a function or just put the derivative of some function, not at a point, but just in general, like the derivative as a function, do x equals x when you do math 8. Okay, I think I forgot a parentheses here. I think there should be an extra parentheses. I got lucky that it didn't mess it up, I think. Hopefully. Okay. Okay, so the reason why, so now think about, these are all kind of names of functions. y1, y2, this is like f, this is g, this is h. So really now, if we want to plug something into this function, n for x, into the derivative really, let's look how to do that. Okay, so we'll do second. So if you look here, we'll do second mode, which is quit. Go to a blank screen. Okay, and one option is to do alpha trace, and then enter, which will get us y1. And then I forgot to do parentheses, so we'll do parentheses. And you really don't need a separate set of parentheses, so that's it. So that's us plugging in. When you do y1 parentheses in a number, that's like f of that number. So all that is plugging in that number into the function y1, which we know is the derivative of f in this case. So this number here is the slope of the tangent line of this function, f, when x equals -2. So this is the slope of a tangent line right here. Okay, so now we want to plug in all the x values from the answer choices. So they wanted us to plug in all the different answer choices were -2, -1. Let's see. Yeah, -2, -1, 0, and 1. So we plugged in -2, so now we're going to plug in the rest. And then watch how you can do this. You can like go up, highlight that, so you don't have to go back to the. Go up, highlight that, and then just change the 2 to a 1, and that's -1. Hit enter. Do it again. Go up, highlight, enter. Change it to a 0, delete, change it to a 0, and then go up, highlight, change that 0 to a 1. Okay, so look at that. So now we got our answer. They wanted to know at what x value of the following values of x, where does it have the greatest slope? So right here, that's the greatest slope. These are all derivatives, so these are all slopes. This is the greatest slope because it's the biggest number. So really, at x equals -1, then our function has the greatest slope because it has the greatest derivative. Okay, so now we know the answer is B. Okay, let's look at different ways to do this though, because maybe for a different problem there would be another way would be better. Okay, so let's look at a different way. I can't remember which way. I pre-recorded these calculator things, so I can't remember what I did next. Let's see. Okay, so next thing is do second window, which is really table set. So what this menu is here is we're going to ultimately get a table, but this is the table setup. And what this is this is going to tell us where our table starts. You know, and when it has a table, it'll just, the first value, the top value is going to be 0, the top x value. And then this tells us how the x values change as you go down. So this says it's going to start at 0 and it's going to go up by 1 every x value that we plug into the function. Okay, so it's going to start at 0, it's going to go up by 1, so the next one's going to be 1, 2, 3, 4, 5, right? So those should be all the x values if we left it like this. And these two only matter if this independent is auto. So remember, independent is like the x value, and dependent is y. So what this is saying is, if we left it like this, it would automatically populate the x's automatically according to the table start and change in table. And then it would automatically give you the x's, and for each x value, it would automatically give you the y by plugging it into the functions that are in y equals. And we'll see that in a second. Okay, but we don't want to start our table at 0. We want to start it at -2. We'll change that. And we do want it to go up by 1, so that's perfect. So we'll keep that the way it is. So just hit second graph, which is table, and then now we can see. So look, these are all the values that we got when we did it, when we plugged them in individually. So maybe a little faster if you have like a bunch of values that you have to plug into a function, in this case y1. Maybe this is a better way. Okay, and then the last way, let's say the table doesn't go up by the same amount. Let's say you just want to plug in some random x values. So you do second table set, and then just change the independent to ask instead. Okay, so now it'll ask for the x value, whoops, and we can just plug it in separately and you get the same thing. So yep, and that's our biggest slope, that's our x value that had the biggest slope, so that's our answer. Okay, so there's 3 different ways to do it, at least that I know of. Yeah. So let's go to the next one. Okay, so next calculator said let f be the function given by this. What's the value of f prime of 2? So I think we won't do the y equals thing. We'll just, from a blank screen. So we really just want to find the derivative of this function when x equals 2. So I think the easiest way to do that is just from a blank screen. Do math 8, and then just plug that function in, e to the negative x. What was it? Yeah, plus cosine minus 1. And then now at the x value, since we only care about one x value, then just do x equals 2. And that's it. So you don't have to go through that whole thing. If you're just plugging in finding the derivative at one x value. Oh yeah, make sure that your mode's in radians when you deal with trig functions, since a trig function was in there. And that's it. So that's the answer. So yeah, if you just want to plug in one x value into the derivative, I would just go to a blank screen, do math 8 there, and then it'll get you the answer. Maybe a little quicker. Sorry about the sound quality. I think not as good. I'm kind of doing this last minute. Okay, so number 10. Oops. They say the figure above shows the graph of a function f, which has a vertical tangent at x equals 4. So we can kind of draw that. 4, there's a vertical tangent line. And the slope of this line is undefined. Slope of that tangent line. Okay, so it has a vertical tangent line at x equals 4 and a horizontal tangent line at x equals 5. Okay. So then they say, which of the following statements is false? So they say, first thing is, f is not differentiable at x equals 2 because the graph of f has a jump discontinuity at x equals 2. So that's true. So that's not it. So the next one, because we want to know which one's false, right? Which one's false? Okay, so this is not false. This is true. F is actually not differentiable at 2 because it's not continuous, because there's a jump discontinuity. Part B, F is not differentiable at 4, x equals 4, because F has a vertical tangent, so that's true, so that's not it either. Part C, F is not differentiable at x equals 5 because it has a horizontal tangent line, so that one is the one that's false. So horizontal tangent lines are fine. You know, the derivative is 0 there. So it is differentiable at x equals 5, and the derivative is 0. You can see D, the last one, f is not differentiable at x equals 7 because the graph of f has a removable discontinuity, so that's true. Okay, just so we can see, so this is, this one is not continuous, that's why those aren't differentiable, and then this one is vertical tangent. Okay, but horizontal tangents are fine. Derivatives are defined at horizontal tangents. So, okay, 11. Which of the following statements, if true, cannot be used to conclude that f of 0 exists? Okay, so just because a certain thing is true, that's not enough to say that f of 0 exists. Okay, so A is the answer. Because just because a limit exists, doesn't mean the function exists. Sorry. Let's do this. All right, so this is, let's say this is the y-axis. So that's the x-axis. Right, so the limit as x approaches 0, that exists because they approach the same thing from the left and right, but the function doesn't exist. So just because the limit exists doesn't mean the function exists. Here, if the function's continuous, then f of 0 exists because that's part of the definition of continuity. If something's continuous at a certain x value, then the function exists at that x value. If something's differentiable, then it's continuous, and so if it's continuous, then it exists. And then they say if the graph of f has a y-intercept, when you plug 0 into a function, that is the y-intercept. So if it has a y-intercept, then f of 0 exists. So yeah, if these are true, then this has to be true. But if A is true, this doesn't have to be true. Okay, 12. So they give us some piecewise function. They say, let f be the function defined above. Which of the following statements is true? So they all talk about it not being differentiable at x equals 5 for certain reasons. Really, this function, you can see, like, if you, let's say you plug in 5 into the bottom function here. So plug in 5 into this bottom one, and you get 6. So from this, you know that f of 5, really, sorry. You know that the limit as x approaches 5 from the right, from values greater than 5, of f of x is whatever you get when you plug in 5 into this, which is 6. But we know from the top one, when x approaches 5 from the left, this function. It just always equals 2. So that means since they don't match, there has to be a jump discontinuity. Oh, I didn't even see that. They didn't even care what type of discontinuity it was, but it's discontinuous. So. Okay, yeah, there's no sharp corner, there's no vertical tangent. It is defined because at x equals 5, it equals 6. So yeah, so just A is not true. Or A is true, sorry. Okay, for the first part of this FRQ. Okay, so they give you a graph of F, and then they give you a table full of basically just certain points on F. Certain of these points, they just give you the exact values, since you can't tell the exact values from the graph. So they say the graph of F, of function F, and a table of selected values of F are shown above. The graph of F has a horizontal tangent line at x equals 2. So there's a horizontal tangent line here. We can mark that just to remind us maybe. Horizontal tangent. Okay. At x equals 2, it's concave up on the interval from 0 to 5. So this is concave up. And it's linear when x is greater than 5, greater than or equal to 5. Okay, so they say approximate the value of f prime at 4.5 using the data from the table. Show the computations that lead to your answer. Okay, so normally what we would do is we would, when you want to estimate the derivative, the slope of a tangent line at a certain x value, and you have a table, kind of pick an x value before and after, and then find the secant line, the average rate of change between those points, your slope of the secant line, and that'll approximate the slope of the tangent line. Okay, the problem with that is if we use these 2 points here, we would be using this point here. I'll draw it. This point here, right? That's that point. And then we'd be using this point here, which is really that point. So do we really want to find the slope of that line that connects those to approximate the slope at 4.5, which is like right around there? Right? We can see like the slope of the tangent line is something totally different than that line. And the reason is because we don't want to use this point that came from the other side of some jump discontinuity. It doesn't make sense. So, okay, so we're not going to use that line 5, 1 because it just doesn't make sense. Okay, so I think the best thing that we can do, since we don't want to use 5, 1, is just use 4 and 4.5. So think about it, if we used the point at 4 and the point at 4.5 and we found that slope, that's technically a secant line, that would be pretty close to the slope of the tangent line at 4.5. So that's a better estimate. So let's do that. So we'll say f prime of 4.5 is approximately f of 4.5 is f of 4. Okay, f of 4.5 that minus f of 4. Okay, let me do this in a calculator real quick. Okay, that's 0.66 on the top. Okay, that's 1.32. Okay, so the slope of the tangent line at 4.5 is approximately 1.32. Okay, so next question. They say for B, they say, is there a value of x on the interval from 0 to 5, the open interval from 0 to 5, such that, this is basically the derivative, right? This is the definition of derivative. So they want to know, is there an x value from 0 to 5, just for this piece here, this little concave up piece? Is there an x value where the derivative equals 0? Give a reason for your answer. So really, we can translate this. When they say this, they really mean when f prime of x equals 0. And then we can even translate that to say when is the slope equal to 0. Right? This is the definition of derivative, so we can write it like that. And the derivative is slope. So we want to know when the slope, or the slope of a tangent line, is 0. Okay, so is there a value of x on the interval where the tangent line equals 0? Yeah, at 2. And the only reason we know that is because they say it. They say the graph of f has a horizontal tangent at x equals 2. So we can write that. Is there a value of x? So we could say yes at x equals 2. F prime of 2 equals 0. So limit h approaches 0. F of 2 plus h minus f of 2 equals over h equals 0. And this is because there is a horizontal tangent at x equals 2. Okay. So yeah, so the derivative equals 0 because there's a horizontal tangent at x equals 2. And if the tangent is horizontal, then the slope is 0. And then that means the derivative is 0. Okay, last part. Let's see. Okay, last part here. They say part C. For each of the following limits, find the value or explain why it doesn't exist. Okay, so let's do that. Okay, so now if you plug in 0 into here, let me make sure we can see this graph. So we'll be paying attention to the graph for the answering these questions. Okay, so think about when this h inside here, so for first part of part C, when this h is approaching 0 from the right, then this inside of f, this thing inside of f, is approaching 5 from the right. Okay, so when this top value is approaching 5 from the right, it's approaching 1, right? Okay, so this equals 1 minus, okay, 1 minus f of 5, which is just, right, which is also, f of 5 is also 1, right? Over 0, so we get 0 over 0, so that's an indeterminate form. Okay, so we can't evaluate that by direct substitution because we get an indeterminate value. Okay, so let's look at another way to do this. So think about, we've got this function. We know what the function is to the right, to the right of like x equals 5. So let's just define this function here. So this is actually, this is wondering what's the slope. This is really saying the same thing as, maybe I'll do it this way. This is saying, see if this makes sense, that this is saying the same thing. What's the limit as x approaches 5 from the right of f prime of x. So what's the slope? Because this is coming from the right of 5. When h is coming from the right of 0, this inside's coming from the right of 5. And we know that this is really definition of derivative, but from the right. This is like the slope from the right. And so the slope from the right is just the slope of this line. And so the slope of this line is 1/4, just doing rise over run. So this equals 1/4. Okay, another way to do it, there are a bunch of ways to do this one, I think. You could also just say what this function is. If you kind of do a little algebra, this ends up being 1/4 x minus 1/4. And then you could actually say, this is really just f of x. F of x equals that. And then now you can actually plug in, use this function as f of x, and then plug in 5 plus h for x, plug in 5 for x, and then evaluate that limit. Okay, but I think this is the easiest way, is just think of slopes. The slope from the right, derivative is slope, and this is the slope from the right, and the slope from the right is this piece, which is always 1/4. Okay, part 2. Okay, so this one you can't do because this one, at least f of 5 existed because there was a point here and it was connected. Here it doesn't exist, or it still exists, but these will be different. Actually, let's actually do this one. Let's do it the same way that we did the first one to start out with. So we'll do limit as h approaches 0 from the right. Actually, sorry. Let's just plug it in. So when we look at, think about when this h approaches 0 from values less than 0, then this inside of f approaches 5 from values less than 5. Okay, so like this top, when function approaches 5 from values less than 5, then that's 4. That equals 4. So this top limit, so this part just becomes 4. And then we see f of 5 is 1. Right, that's just evaluating the function. And then when you plug in 0 into the bottom, you get 0. So you get 3/0. So remember, before we got 0/0, which is an indeterminate value, which means we had to do more work. And this is the more work that we did. Here, you don't do more work. Whenever you get something over 0, that means the limit doesn't exist. And if the limit doesn't exist, since this is a definition of derivative in terms of a limit, if the limit doesn't exist, then the derivative doesn't exist. Okay, so this is not differentiable. That, not differentiable. It's D and E. Okay, last one. If these limits don't match, then the overall limit, really if from either side it doesn't exist, like in this case, you can also say it doesn't match, then this won't, the last limit won't exist. So this is definitely D and E. D and E, you could either say because limits don't match, or it's really because limit from one side doesn't exist. Okay, that should be from the left. Sorry. Okay, so that's it.